Hello everybody. So we'll be starting the videos for the second chapter of the course, that is about the linear time invariant systems. And in the last chapter, in the last few videos, we studied some of the properties of the systems, properties like linearity, invertibility, causality, time invariance, stability. Then we also studied the memory requirement of the systems, right? And accordingly, we classify the systems based on these properties, right? So, second chapter starts with the discussion of a special class of systems, what we call linear time invariant systems. And as the name suggests, these are basically the systems. So, these are the systems that satisfy the property of so they satisfy two properties. One is linearity, which basically means they follow the property of superposition. Fine. Please remember the property of linearity when we discussed in the last videos, and that it basically is a system which follows the property of superposition. And superposition itself involves two properties. One is additivity and the other one is the scalability. So these are the systems that are linear. They follow the property of superposition and they are also time invariance. Right? So we assume that these systems, they are linear and they are time invariant, hence the name linear time invariant system. And this kind of assumption is pretty valid, it's pretty logical rather, because most of the real world systems, in our domain, the electronic systems, like if we take simple systems like diodes, transistors, if you have done their characteristics, you will observe that there is a certain range of operation where these systems are linear, and same goes true for the time invariant. So it's a pretty valid assumption. ऐसा नहीं है कि haphazardly we have assumed that we'll assume that a system is linear, this system is time invariant. It's not like that. Is that कि जो भी आपके physical phenomenon है, जो real world phenomenon है, जो आपके electronic systems है, there is a certain range of operation where you can assume that they are actually linear and time invariant. So we come up with a special class of systems wherein we assume that these two properties are satisfied, and we define a linear time invariant system. Fine. So in this chapter, what we're basically doing is, with these two assumptions, that assuming that our system is linear time invariant, we're first trying to characterize them. Obviously, mathematically, how do we represent these systems? Then using that mathematical characterization, we will then discuss different properties of these LTI systems, right? So we will be discussing the LTI system under two headings. We will be discussing continuous time LTI systems, and then the discrete time LTI systems. Fine. So this was the basic classification that we used in signals, and your system is also defined in terms of your signals. If you just recall the classical definition of your system, it is a transformation of an input signal, fine, through a series of operations. Right? So there's an input signal, there's an output signal. Right? So if your system, it has an input signal and output signal which are continuous in time, we say it's a continuous time system. Right? And if it's, so this will be a continuous time system. And if it's something like this, where in the output sequence, output signal and the input signal, they are both discrete in time, so we say discrete time system. Right? So we're studying LTI system under two separate headings: continuous time LTI system. We'll see how they are characterized, then how do we decide on the properties of these LTI systems, then we'll be taking on the discrete time LTI system. And as expected, you will see that you can generalize the results. There will be a lot of, you can see, resemblance between the analysis when we analyze them separately. Anyways, we'll be analyzing them separately, and you will see there that there will be the degree of resemblance will be high. Okay, so we'll start with the continuous time LTI systems. So our initial analysis will be for continuous time LTI systems. Right. And another thing you will observe here, that whatever you have learned in the first chapter, the concept you learned there, how we define a signal, what are the basic signals that we use in signals and systems, what are the different properties of this, especially the properties of the system part, you'll have to apply it here. In fact, throughout for the rest of your course, इसके बाद immediately we'll be taking the frequency domain rather, where we'll be going for Fourier analysis, then Laplace, then Z transform. But the basics you cover here in the first chapter, you will see they will repeat themselves in different forms in these subsequent chapters. Right? So we'll have to use a lot of stuff that we learned in our first chapter. And in the first chapter, we learned an important, it was basically one of the basic signals that we discussed, and it was the impulse signal. So just for your remembrance, I will mention some properties of this signal. So we discussed impulse signal in the continuous time domain as well as in the discrete time domain. Discrete time domain, it was pretty straightforward, but for the time being we are doing the continuous time LTI systems. So our impulse signal in the continuous time domain, it was characterized, it was defined by these two mathematical expressions. Delta t is equivalent to 0 for t is not equivalent to 0. Then to add the continuity, this function, this signal also satisfied this relation, that if you take the integral of this continuous time impulse signal, it will be unity. Then I had also explained how we graphically visualize this signal. It is basically a limiting case of your rectangular pulse, as the width tends to 0 and height tends to infinity, and area remains the constant. Right? We had also mentioned some peculiar properties of this impulse signal. For example, from this particular part of the definition, we can come up with a generalization that if there is a general signal x of t, you multiply this signal with delta t, it will give you x0 delta t, right? Because delta t is equal to 0 for t is not equal to 0. Obviously, it means that there will be only one point where your signal x of t will persist, that is x0t, fine? x0 into delta t. Then again, we can generalize that if you have the same signal x of t and you multiply it with a shifted impulse signal, something like this, then you will get x of t naught into delta t minus t naught. So this directly follows from the first part of the definition, right? Then the second part of the definition, which basically takes this thing into consideration, that if we take the overall integral, and it will be equivalent to unity. So if I include this also, then we get a generalization that any of your arbitrary signal x of t, it can be actually expressed as a product. I'm using a dummy variable tau, t minus tau d tau, right? So what you're doing is you're taking a signal, multiplying it with a shifted impulse, right? And then integrating over the limit of tau. So it is something like this. For example, tau is equivalent to 0. You will be getting x of 0 into delta t. Then tau is equivalent to 1. It will be x of 1 delta t minus 1. Tau is equivalent to 2, x of 2 delta t minus 2. Then to sum up the whole signal, you just put an integral that include all these components corresponding to individual values of this tau. Right? So what I'm trying to say here is any of your arbitrary signal x of t, it can be expressed in terms of an impulse signal. Right? Now don't get confused with this tau. Like I said, it's a dummy variable, but physically it again means a parameter which is related to time, yeah, which is time in itself. Right? So this is something we covered in the first chapter. Right? It was basically these three properties, and they were derived from the definition of the impulse in the continuous time domain, the mathematical definition itself. Okay. Now let's start with the continuous time LTI system. Fine. So we start with basically this thing that a continuous time signal, any continuous time signal for that matter, say x of t, it can be expressed in terms of an impulse function. Right? So it can be expressed in terms of an impulse function. Right? So I have some arbitrary signal x of t, and I'm expressing it in terms of an impulse function using this integral. Let's call it 1. Right? Then we have a system. Let's consider a system that has a system function, a system property, say t. Fine. Now to this system, I'm applying the input delta t, that is, I'm applying the impulse signal to this system. Now depending upon the system property t, it will give some output. Fine. So let's call that output h of t. Fine. So here h of t is the response of a continuous time system. Since we are dealing with LTI system, so let me be specific that this thing here, it is basically an LTI system. Fine. That's why I have just to differentiate it with the normal system. If you remember, we used h as the system function. Since this is an LTI system, so I will be using a t to represent the system property. So let ht be the response of the continuous time LTI system to an impulse function. Fine. Then we can write that h of t is equivalent to the transformation t acting upon delta t. Let's call it 2. Fine. Now the response of the same system, we are considering this LTI system having the system function t. Now to this system, I will apply my actual input x of t, and I will get some output y of t. Okay. And again, this thing will be mathematically represented as, okay, we will have y of t is equivalent to the transformation t acting upon the input signal x of t. Right? But we have expressed x of t in terms of my impulse function using the equation 1. So if I put out that substitution, so I can say it is the transformation acting upon the integral minus infinity to plus infinity x of tau delta t minus tau dot tau d tau. So I'm using the generalization here that is signal x of t, it has been expressed in terms of an impulse function. Right? So let's call it 3. Now, I'm assuming my system is LTI system, which means I'm assuming it is a linear system. That means it follows a superposition principle. So we are assuming, so let me write it here. Since the system is linear, which is represented by equation 3, this system is linear. It will follow the principle of superposition, which means it will follow this principle of additivity. It will follow the principle of that scalability or homogeneity. So what I can do is, क्योंकि linear system, had it been a non-linear system, then जो operation में करने वाला हो, we couldn't have done that. But since this is a linear system, I can take this operator t inside the integral. Fine, something like this. This is only possible if I assume the system is linear. Right? So operator co-op, you can take it within the integral. Right? And then again, we know that this thing, transformation of delta t minus tau, is, yeah, let's do one thing. Let's call it 4. Fine. And I will add a few more steps so that it's clear. Fine. Now, this is from the system property that it is linear. Also, our system is time invariant. The system is time invariant, and it means if I have this system, I'm giving an input delta t. In response, I'm having an output h of t. If I shift my input by some amount, say instead of delta t, if I give delta t minus tau, but since the system is time invariant, your output will be t minus tau. Right? So transformation of t, this, you can replace this by h of t minus tau. Okay? So if we do this substitution, what we will be getting is this, that y of t is equivalent to minus infinity to plus infinity x of tau, then h of t minus tau d tau. Fine. And this equation 5 it's known as convolution integral. It is basically a mathematical operation, what we call the convolution operation. And this equation basically it characterizes equation 5 convolution integral. So you can say convolution integral completely characterizes a continuous time LTI system. Fine. And an important part of this convolution integral is this impulse response. So I can also deduce that an LTI system is completely characterized by its impulse response. Right. So stop here. Next video we will look into the further implications of this convolution integral.